Hi, and welcome to the second lecture of semantics. So let me give you a recap of what you actually saw in the last video. I introduced to you what semantics is, and I said what we are going to be doing is natural language semantics. And I introduced the semantic intuitions of equivalence, contradiction, entailment, and semantic ambiguity. Now, what we are going to be doing in this video is I am going to be showing you how you can actually test whether each of these kind of formula that I put up on this lecture slide can be tested with using formal logic and truth tables. So remember, we talked about compositionality in the last video. And so what we are going to be doing for compositionality is how do actually the meanings of these individual parts actually combine together to give you the meaning of that particular sentence. We already know the meaning of individual phrases from syntax, so we know what a VP is, we know what an NP is, we know what a CP is, etc. But what we don't know yet is the meaning of all these operators such as and, or, and not. And so that is what is going to be the focus of this video. I'm going to be introducing the meaning of what is not, what is and what is or, and how do you actually use these to get to the meaning of entailment, equivalence, and contradiction, etc. So let us refine what we did in the last video. Now, when you look at any sentence A, say Mary swims is a sentence A, you can see that the negation of A is also going to be you just take the sentence and insert in the negation, right? Mary does not swim. So you can similarly, you can conjoin any two sentences and you can disjoin any two sentences. Mary swims and John jogs is a conjunction, and or is a disjunction. So Mary swims or John jogs. Now, the meaning of these individual sentence operators is what we are going to look at. And I'm going to color code this for the rest of the video. So blue is always going to be negation, red is always going to be and purple is always going to be or. Now, when you look at we'll start with negation. So when you look at negation, the not, you can see that the not itself does not appear to have a lot of content, right? Not always attaches to another sentence, and that's really when you get the meaning difference. When you look at and, well, and is true only if both the sentences that it conjoins is true, right? So when Mary swims is true and John jogs is true, then you get A and B is true. With or, the meaning is slightly different from and. If Mary swims is true but John jogs is not true, A or B is still true because of the truth value of sentence A, right? So knowing what sentence conjunction, disjunction, and negation is, it amounts to understanding what each of these individual operators actually work with. What is the meaning of these individual operators? And so to do that, I am going to introduce to you formal logic, a very fundamental formal logic. And we always start in formal logic by defining what a proposition is. A proposition is what we call a declarative sentence, right? So the declarative sentence, it is always in the positive. So that means even if you have a negation, the negation is an operator. So the proposition is the sentence in the positive, right, without the negation. And each proposition has two truth values. It can either be true or it can be false, right, but not both. Right? So one sentence can only have one truth value at one time. We use small caps, right? Small case letters to denote propositions. So we start with P because the first letter of proposition is P. So PQRS, but it doesn't matter. Any small case letter can be used for a proposition. And then we use logical connectors or logical operators, or what we just saw before, the negation, not, the conjunction and the disjunction, or to form compound propositions. So we are going to start with the basic truth tables for and, not, and or. We'll start with the negation, because that's easiest. Negation in formal logic is written like that, right, as you can see. So this is how you would, this is the symbol for negation, right? So when you say negation of P, that is read as negation of P, right? So For any statement P, for any proposition P, negation of P is false if P is true. So let's start by drawing a truth table. We draw two columns, right? There's a column for P, the proposition, and a column for the negative proposition, which is negation of P. When P is true, this is how you read the truth table, right? So when P, your proposition, is true, the negation of P is false, right? And when P is false, then negation of P is true. So you always get the opposite truth value. If P is true, negation of P is false, and if P is false, negation of P is true. Let's move on to the truth table of AND. AND is written in formal logic as the upside down V symbol, right? So it's written like that. That's AND in formal logic. Let's look at the truth table for conjoining together two propositions, P and Q, with the AND symbol. So here is a truth table for P and Q. So when you combine P and Q together, remember that each proposition has two truth values, true, false, right? So when you combine two propositions together, P and Q, what you get is 2 raised to n number of truth value combinations. So n equal to 2 over here, propositions, 2 propositions, P is 1 proposition, Q is 1 proposition. So 2 raised to n equal to 2, 2 raised to 2 equal to 4. And that's why you get 4 rows over here, right? So P is 1 column, Q is 1 column, and P and Q, which is the conjunction. And so the truth value let me do this in a Word document so that you can see what I'm talking about. So if you have a proposition P, the small p, I'm going to use the curly brackets to denote a set. So P is a proposition that has 2 truth values, true and false. Similarly, Q is also a proposition that has 2 truth values, true and false, right? Now, a note for secondary ed math students, if you have been using for the binary truth values instead of T and F, if you've been using 1 and 0, be my guest. You can do that for the assignment and for the finals. I'm going to be using T and F this semester, and you can, use whatever is most comfortable for you, either T and F or 1 and 0. I don't have a preference. So if you have P and Q as 2 propositions, you get 2 raised to n. N stands for the number of propositions, n equal to 2, right, over here. So therefore you get 2 into 2 equal to 4 truth value combinations. So the truth value combinations between P and Q are true, 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 false, false, true, and false, false, right? True, 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 false, false, true, and false, false, right? So that's the way that I get these different permutation and combinations for truth values, right? True, 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 false, false, true, and false, false. When you conjoin P and Q, remember earlier we talked about how P and Q is true only if both P is true and Q is true. The easiest way for you to remember this, if you're not a math person, is for you to remember an English sentence, right? So take P is Mary danced and Q is John swam. P and Q is true only if both Mary danced and John swam. So true, true, therefore true. All other cases, true, false, false, true, false, false, P and Q is false because the truth value of conjunction says both the propositions have to be true. Let's move on to the basic truth table of OR. OR is written as the V symbol, right? And therefore, it's very easy for my students to get confused between the upside down V symbol, which is and the V symbol, which is OR. if you get confused, just write or and instead of using the logical, kind of symbols. But I will expect you to have some kind of familiarity in reading these, right? So it is good for you to have some kind of a way to remember that this is or and this is and. Now, what P or Q says is that either P is true or Q is true for P or Q to be true, right? So the fundamental truth table for P or Q is different from P and Q. And I also have a note here that there are two kinds of or in English. There's one called the inclusive or and the one called the exclusive or. We are only going to be dealing with the inclusive or. You don't have to worry about the exclusive or for the basis of this class. So here's the truth table for the inclusive or. You have the same truth values as before: true, 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 false, false, true, and false, false. And then you have the P or Q, which is true, 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 and false, right? The only case where you get false for P or Q is when you have two truth values that are false for P or Q. So that's what I've kind of given you, right? If you take the set true and false, right, that's what it means. Anything in the curly bracket is a set. And therefore, you can actually now define the operators as follows. The symbol that I used, right, the negation symbol, the and symbol, and the or symbol. And then you can use it, negation of P, P and Q, P or Q. And then it is read as not P, P and Q, P or Q, negation, conjunction, and disjunction. Like I told you, we're only going to be talking about the inclusive or. The exclusive or is seen in cases such as I'm either walking or driving to work today. As you can see, I'm either walking or driving to work today is not true when both the P or Q are true, and therefore you get a slightly different truth table for exclusive or, but I don't want you to be worried about that. I just put this note here in case somebody's wondering about what is the exclusive or, right? So now we know the fundamental meaning or the basic meaning of the conjunction operator, the disjunction operator, and the negation. And now what we are going to do is we can actually test the hypothesis for entailment, contradiction, ambiguity, and equivalency, right? Now, I'm not going to be doing ambiguity because when you get your final exam review, you will see that I have taken out cases where there are more than two propositions because it tends to be a little complicated for people who have not done formal logic before. So I have it in here, but we are not going to be seeing the testing of the ambiguity because I just don't want to confuse you more. So we are just going to do entailment, contradiction, and equivalency in this video. So here is testing entailment. We want to test P and Q entails P. So now this is a truth table that you have seen before for the conjunction operator or and you can see that each of these rows can be situation 1, situation 2, situation 3, and situation 4, and you can see that when P and Q is true, that is the first row, situation 1, that entails the truth of P, right? So therefore, P and Q entails P is true, right? To test contradiction, we have again the same truth table as contradiction. So you have P and the negation of P, and you can see that you have only two situations over here because there are only truth values associated with one proposition. So when P is true, negation of P is false, and therefore situation 1 is enough to test that when P is true, negation of P is false, and therefore P contradicts negation of P. To test equivalency, this is when you start to see that you can actually build more complicated semantic truth tables. So we are going to see negation of P or negation of Q is equivalent to negation of P and Q, right? So the way that we start with is we always start with the left-hand side and then finish the left-hand side and then proceed to the right-hand side. So this, what you see right now is the truth table for the left-hand side, all right? So this is negation of P or negation of Q. So you start with P, Q, and then what you do is you proceed to do anything that's in the parentheses, right? So you do negation of P, which is what I put in the third column, and then negation of Q, which is the fourth column, and then I have put the right-hand side, which is negation of P or negation of Q, and the rightmost column. Now, what you do is you start with true, 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 false, false, true, and false, false, right? And then to do negation of P, what you do is you look at this column, right? You look at column A, and you use the semantics of the negation operator to fill in this column. So when P is true, negation of P is false. When P is true, negation of P is false. When P is false, negation of P is true. When P is false, negation of P is true. Then you go on to this column, this is Q, and so negation of Q means take column B and you negate entire column Q.